The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello everyone, and thank you for joining our finale session today for the 2023 AI, ML and 5G Challenge hosted by the ITU, the International Telecommunication Union. My name is Mia Nishio and I will be moderating today's session. The Machine Learning in 5G Challenge, now in its fourth year, aims to create a community to solve network-related problems using machine learning. This year, the challenge featured 12 different problem statements, all relevant to the updates and progresses we've seen in both AI and communication networks. In general, we saw a great increase in participants from nearly 100 countries across the globe, and the presenters today are those who've scored the highest in 3 different problem statements. We have a very exciting hour and a half ahead of us, so I'd like to first call for Professor Kanai from the University of Tokyo to make opening remarks and kickstart the session. Over to you.
Okay, thank you for the introduction, Mia. And good morning, good afternoon, and good evening, everyone. My name is Kenji Kanai, and I am an assistant professor at the University of Tokyo. Before we start, I appreciate all the participants joining today from the locations worldwide. So, as Mia said, that the ITU AI/ML Challenge, 5G Challenge in 2023 offers a platform for collaboratively addressing the problems in applying the AI/ML in communication networks, including the 5G, beyond 5G, and also the 6G. So the challenge connects participants, students, and the professionals from the more than 100 countries with industry and academia, solving the real-world problems using the AI/ML in communication networks. Today, we've introduced the exciting problem statement, the 3 problem statement, multimodal V2V prediction, depth map estimation in the 60 mmWave systems, and the 3D location estimation using the RSSI of the wireless LAN. To solve the problems, the 5 best teams survive, and they will give the presentations to demonstrate their outstanding solutions. So let's start and enjoy the presentations. Thank you very much.
Thank you very much, Professor Kanai. I am just going to share my screen. Hopefully that is shared.
Yeah,
I'm just going to be giving a brief overview of the 2023 ITU AI/ML and 5G Challenge for the 3 problem statements, as Professor Kanai mentioned. This is just the agenda of my presentation. I'm going to be going over the challenge overview, as well as the statistics for this year, and finally the ITUT special journal. So as Professor Kanai mentioned, we are going to be presenting for three different problem statements. The first is multimodal V2V beam prediction from Arizona State University. Next is depth math estimation in 6G millimeter wave systems from NIST, and 3D location estimation using RSSI of LAN from the from Rising. We had 77 teams enrolled overall, with 91 participants and 15 teams submitted this year. So we had 12 different problem statements in 2023, and as mentioned already, the Arizona State University, NIST, and Rising are the hosts of the problem statements for the presentations today. As always, this year we had prizes and awards from ITU. First place winners will be receiving 500 francs. Runner-ups, so second place, will be receiving 300 francs, and third place will be receiving 200 francs alongside a certification. Again, we'd just like to say thanks again to all the hosts who provided problem statements for this year, as well as our technical partners who made the challenge possible. And last but not least, I'd like to mention especially to the winners of this year's challenge that we will be having a new special issue for the ITU journal. We'd like you to hopefully prepare your manuscripts and submit by the deadline, so January 2024. Our leading guest editor will be Paul Harvey from University of Glasgow, and we'd be very excited and happy for you to make your contributions to this journal. This is just the agenda for today's finale session. We're up to hear the finale presentation right now, and then we'll be going on to the participants' presentations. We'll be having a brief explanation from each of the hosts, an 8-minute presentation, and then a 4-minute Q&A session. We'll be making some brief announcements before closing off today's session. I'd also just like to mention that you can interact with us and other participants on the Challenge Slack channel. So if you're interested in joining, or if you're interested in talking more about the presentations that you'll be seeing today, please make sure to join. Without further ado, I'd like to first call for Professor Kanai to explain this year's problem statement from Rising.
Okay, thank you very much for the introduction. Again, welcome to the ITU AI ML Challenge, 5G Challenge 2023. And my name is Kenji Kanai, and from the University of Tokyo, Japan. So today I would like to briefly introduce the problem statement from the Rising regarding the 3D location estimation using RSSI of the world's RAM. So our problem statement is organized by the Cross-Field Research Association of Super Intelligent Networking, we call the Rising. Rising is a special ad hoc committee of the Institute of Electronics, Information and Communication Engineers Communication Society in Japan. The purpose of the Rising is to introduce, discuss, and gather information on research of the intelligent communication technologies and systems with AI. So before I introduce the problem statement, I give the background. As you know, the demand for the location information is becoming more important, popular, due to the emergence of the map applications and social network services like Google Map, Instagram, and Twitter. And also the augmented reality and the virtual reality is also very popular. So the mainstream of the localization for many years is we use the global positioning system, GPS. So GPS, for realization of the localization, GPS needs more than 4 satellites are required. However, if the number of satellites that can be seen from the receiver decreases, we know that its accuracy significantly degrades. So the new proposal, the radio signal is one of the very good candidates to give the accurate localization as well as DPS. So received signal strength indicator, RSSI, indicates how strong the signal transmitted from the specific transmitter is received at each position. So currently, there are the two major approaches based on the RSSI the localization. So first one is RSSI map-based localization, and the second one is range-based localization. So this challenges aims to verify if the artificial intelligence or the machine learning aided the 3D localization utilizing the RSSI can achieve similar accuracy as the GPS-based localization. And we would like to explore the possibility if the data-oriented localization can replace the model-based localization. So in this year, we collected the 4 kinds of the radio signals from the 4 access points. So as you see in this image, we collected the 4 access points. We collected the data from the 4 access points, which are located at the different heights. And the receiver's signal power, RSSI, was measured in several frequencies, including 2.4 gigahertz and 5 gigahertz. And also, you can see that the location of the access point and the measurement points were obtained by GPS, and some measurement data were missing due to the anomalous environment. From the collected data, we defined the training data. And the training data contains 3 information. First one is the information about the access point names, SSID, and etc. So second, information from the receiver data, like a timestamp and also the RSSI. And the final one is the information about the surrounding environment, like map information of the measurement area and also the loss or anomalous condition of the communication link. So all these data, we defined the training data and we provided to the participants. After that, the participants develop their own solution using the machine learning or AI technique, and they evaluated these 4 kinds of the evaluation metrics: the evaluation localization, average localization error, maximum localization error, and the algorithm performance, like a computational complexity. And the final one is a future direction of improvement of the proposed algorithms or techniques. So here is the evaluation process. As I said, the participant developed the program and tuned the AI or ML models, localization algorithm, and the parameters using the training data. And they submit all required materials and location results using the first dataset to the administrative office around October 27th. After that, we select the top ranking teams, and the selected teams will perform the localization based on the second test dataset during the grand challenge finale. So here is the evaluation method. Each team is requested to perform the localization based on the test dataset without the GPS information. And the top teams are supposed to compete by using the second dataset provided just before the final competition. And after that, we finally decision that the Team Paris is the best team among the 20 registrations. So now I will introduce the Paris, and he will give a great presentation about their solutions. Okay, so I will hand off the Team Paris, and if you're ready, please start the presentation.
Okay, thank you. Let me just share my screen, start the presentation. Can you see my screen?
Yeah, great.
Right. Okay, so as introduced, this is the challenge on estimating the 3D location using the RSSI of a wireless LAN. So a quick overview. So the RSSI is just a measurement of power present in the received radio signal, so which is mostly invisible to the receiver. So the wireless LAN, in this case Wi-Fi, is obviously not designed for the purpose of positioning. However, we can use the signal strength to find a location of a receiver. So there's no direct mathematical formula to get a location. So hence, employing machine learning techniques. So, right, so this is the setup of the data that was provided. So we have RSSI, which is measured in decibel milliwatts, and other auxiliary information. Time series GPS data, channel setting, frequency. This is a quick 5-row display of the data set provided. So we can see we have latitude, longitude, and receiver height. This is exactly what we should train the model to be able to estimate. So we can see we have 3 values to predict or to estimate. We can see they're in very different ranges. Latitude goes on 35 point, longitude 136, and the height is 1.9 and so forth. So I'll explain something about this trend here in a bit, but that was the setup of the data provided. So there were 4 access points as shown in this diagram here. More on that later. So the solution I came up with was first to deal with the RSSI, which is our main value to estimate this particular, the 3D location. So RSSI usually ranges from negative 100 to 0, and sometimes to positive 100. But our data, based on various devices, our data ranges from negative 80 to negative 44. So I had to find a way to represent this in different ways, meaning transformation. So I made 2 transformations, as you can see here, 0 to 1 normalization and power normalization. So power transformation, sorry. So from the negative 80 to negative 44, we had a power transformation that gave us a range from 0 to 0.07, the 0 to 1, which is supposed to give us 0 to 1, but yes, we are not covering the whole range, so it makes sense that the values that we came up with was 0 to 0.4. So this is the original distribution of the RSSI, and these are the transformations. So this should add information for the machine learning model. Going forward, so we cannot only process the RSSI, there's also the other information. We can also deal with them. So access points, we said we have 4. So the distances between each point should be important in giving us the information about latency and possibly the time of arrival to a particular receiver. So I calculated the distances using the Haversine distances, the Haversine formula of each and every access point to another access point. Also, we had time, as you can see here, represented in Unix time. So the range was 3 hours, so there was not so much to do with that. So I used a lag step of 1 to match the record step that was provided for the data. So this should give us some relationship with the time of arrival of the signal. Miscellaneously, I also had to pivot the data on channel so that I can have the RSSI with respect to particular channel and particular APs, as you can see here. So yeah, so that was the processing step. Nextly, I had to come up with an algorithm that should work well with this particular data. So I used the hist gradient boosting. So this is a gradient boosting algorithm, like gradient boosting, XGBoost, or CutBoost. But the way this one works is it runs by binning the features. So the nature of the data actually supports this particular algorithm, because as you can see here, these frequency channel are supposed to be numerical. They are numerical values, but we have like very few unique values of them. Okay, so they are in a sense categorical. So in a sense that binning them should not be a problem. That's why histogram boosting was the best algorithm for this. So another thing was, because we're predicting 3 particular values with different ranges, so it was necessary to make 3 different regressors for each target. So latitude had to be 3 different regressors for latitude, longitude, and the height, so that the model doesn't have to generalize about the ranges from each of the 3 targets. Right. So the training mode I used was stratified payfold. I stratified with respect to the receiver height, and also I also did a 1 batch train to see how it performs. So how did I evaluate my my approach? So I calculated when I get a 3D location, I calculate the 3D distance from the predicted location to the actual location. So this is using Haversine distance, the Haversine distance, and the Pythagoras theorem. So this gives us the actual error in meters in 3D space. So these are the results preliminarily with the data provided. We had a training size of 7,100 samples and test of 7,200. So these are the distributions of the errors in distance in 3D space in meters that was given out by the model. So okay. So training on 7,100 and evaluating on 7,200 samples, we had an average error of ranging from 2.7 meters when it's trained on single batch, and 6 stratified folds, 2.8 meters. So you can see this particular distribution of the errors. Yes, most lie in 0 and goes along well to 10, and then we have some values at 16. Same to the SK fold. So we have a problem of a maximum error stacking at 16. Right. So I tried to increase the train size, finding the whole data and just taking 75% as train and 25 as test. The single batch, yes, reduced well to 0.5 meters. And for the single batch, yeah, and the stratified got to 0.4 meters. We can see the particular distribution plots. A lot of values now lie at 0, but we still have the problem of a maximum error stacking at 16. So this, signified some problem within the data set. So I went on, when provided this with the final data set, so I used exactly how it was provided, final for train, all of it, and final for test.
1 minute.
All right, thank you. So this is the distribution when passed to the 3 regressor model. Still, most of them lie at 0, which is a good thing. And at this point, we had a maximum error of 6. So there was some kind of an issue with the maximum error staying at the same point. That was 16 and this was 6, which when I came to analyze further, it was about the data set. So conclusively, we address the estimating 3-dimensional location in wireless LAN. So contributions for these would be transforming the RSSI and extending the features from the few that we had, and using a 3-modal approach to provide the 3-dimension location of the receivers. That should be it. Thank you.
Okay, thank you very much. Oh, Mia,
Thank
is
you
it
very
on?
much for your thank you very much for your presentation. I'd like to go into Q&A session. Yes, Professor, if I could ask you to ask a few questions.
Thank you very much for the very interesting talk and very practical solutions. So I'd like to, I have one question is how about the complexity of your solution? So is it run on the real time or the several minutes to estimate the locations?
Well, I know. Well, complexity is one of the things that I was considering in building this. So it's very simple, actually. It takes a very short time to run. I didn't record the time it takes because it was so like less than 40 seconds. So obviously it's yeah.
So running only on the CPU.
So and that is estimating on more than 7,100 samples. So if per sample is milliseconds, you have a target. Yeah.
Okay. So you currently only using RSSI and related information like channel information and also I think the frequency, right? To build a model. So to improve your so currently the error is very small. So only the less than 1 meter is very practical, I think. But how about how to improve or how to say that reduce the maximum error? What kind of the information we can use additionally? Do you have any ideas?
Well, one of the things I was thinking about was if we could have for a new data set, maybe if we're trying to collect a new data set, if we could have the time, like the timestamps for recording the data, sending signals and receiving signals, so we can have the difference, something like that. That would tell us something about the time of arrival.
So that kind of the feedback is very, I think, the important thing. I think to like next year's problem statement, creating the next statement. So so about your solutions. So what is the most important key techniques? What is the key techniques? So about the data processing or another things or something.
So I think I can name 3 because when I came up with something, I try to do it without it so that I can see what it changes. So the transformations were actually very important because when I did the pivoting to get the particular RSSI for a particular channel, I didn't use the actual RSSI. I used the transformed RSSI. So that was better than the actual RSSI. So that's one. And also, I didn't post-process the targets. I left them as they were. Then that's why I used 3 different regressors for each and every target. I mean, component of the target. So that way you don't have to generalize. The model just has to focus on its one particular range of values. Yeah. So the 3 regressors without post-processing the targets and the transformation plus the pivoting with the particular channels and the APs.
Interesting. And the last one question is that so I think that there are some data set inside the dataset there are some noises. So I think that this noise makes the bigger errors. 16 meters, I think. The maximum error is very big. So
Yeah, sure.
this is, I think, the dataset problem, I think. But what did you analyze?
Yes, I did. Initially, I didn't deal with the outliers. Then when I saw the 16, I thought, okay, this is obviously something has to do with the outliers. Then I dealt with the outliers at different levels, but the 16 stuck. So I had to wait for the other data set, the final, and so whether okay, something that just stays forever or yeah. So I think it's in the general trend of the data that there's some maximum value that stays there. But in general, I think more time is needed for that. I think.
Okay, I think
thank you very much. Yes, time is up. Thank you very much.
Thank you very much.
Okay. I'd like to next call for Steve. We're going to have an explanation and presentation for the problem statement depth math estimation in 6G mmWave systems from NIST. The floor is yours.
All right, I'm gonna give a short introduction on the problem statement. So the background of the challenge is basically wireless sensing. That is basically the process of acquiring information using wireless signals. And there are several technologies available already, like using radar, FMCW radar, or ultra-wideband, but also there are new ideas like using communication systems like 6G or Wi-Fi to perform sensing. So besides the communication aspect, also acquire information about targets or environment. And that's possible thanks also to advancement in computing, such as the use of AI and ML. So we are going towards, implementation of wireless sensing using everyday devices. And in this context, we are talking about integrated sensing and communication. So this is a little bit the background of the challenge. And the idea is basically to reuse everyday device to create a digital twin. So we start from the physical world. We have an observation of the physical world, and we want to digitalize it using everyday devices, so integrated sensing and communication, and with the aid of an AI and ML. So creating the digital world will allow to perform, for example, online simulation, estimation, and inference of problems that we will do otherwise in the physical world, probably spending more time. So the idea is to take a snapshot of the physical world, go to digital, to solve some problem, and then apply those what we learn in the digital world to apply those results in the physical world. So for this challenge, we propose a dataset that was measured in an indoor environment. We had a transmitter and a receiver moving around the room. The signal was sent at 60 gigahertz, and we collected measurement at different locations. So you see here the trajectory of the receiver. And we provided two of these dataset collected for training the algorithm, and with the third we evaluated the solution. So the dataset consisted of camera, LiDAR, and RF data. For this challenge, we just used RF data that are basically multipath component, including angles, azimuth and elevation, and delay and path gain, of course. And we provided also the LiDAR. So for training, we provided LiDAR and RF, but for evaluation, we just provided the RF. So what we asked in the end, it was to design an AI/ML model that, given an RF signal in input, will provide a LiDAR-like point cloud. And of course, with the real LiDAR data that we collected, we did the evaluation. And an important remark is that training and evaluation data set are collected in different areas of the room. So that's a first step towards scalability of a machine learning model where the let's say training data set has not been collected exactly in the same position in exactly the same condition of the evaluation. And the evaluation metric was the chamfer distance, that is a distance that allows to compare to different point cloud. So basically, we take one of the point cloud as a reference, we compute the minimum between the other constellation, the other point cloud to the reference, and we compute the distance of those points, and then we do the other way around, assuming the other point cloud as a reference, and that allow to compensate for different points, for example, in the estimated and the given point clouds. So based on this evaluation metric, we ranked the team, and today we have the team that was evaluated with the best distance or with the smallest distance. So with that intro, we can go to the solution of the challenge.
Thank you very much. Can we call for team Jaya?
Yeah. Hello, everyone. Share my screen. Hello, everyone. I'll be presenting our solution model for the problem statement based on the depth map estimation in 60 millimeter wave systems. I work as a research engineer at TCS Research, Bangalore, India. The brief agenda of this presentation is I'll begin with the motivation of why this problem statement is interesting, followed by the measurement environment that the NIST has used to collect the data, then followed by the solution model, and finally presenting the results. To begin with, as Steve mentioned, for the digital twin thing, depth map estimation is one of the critical component, and using the millimeter waves for the depth map estimation means we are using the same spectrum and hardware for both sensing and communication. And this is nothing but the integrated sensing and communication technology. And apart from this depth map estimation of the indoor environment, there are other applications of ISAC, which are high accuracy localization and tracking, gesture and activity recognition, simultaneous imaging and mapping. The problem statement for the that was proposed by NIST, we need to estimate the depth map of the indoor environment using the millimeter wave signals with a stationary transmitter and a mobile receiver. And for this, channel impulse response of millimeter wave MIMO channel was given, and also the LiDAR data was given. But the LiDAR data has to be only used during the training of the model. The challenge is to propose an AML model for this depth estimation. And this is the setup that was used to collect the data, which has the antennas as well as the LiDAR and also the camera. And the measure environment that was considered was they considered a stationary transmitter, which consists of a uniform planar array of size 8 cross 8, and a receiver which can move in the indoor environment. And the receiver also contains a uniform planar array. The receiver is also equipped with the LiDAR to collect the LiDAR data. And this data is collected using a 3D double directional 60 gigahertz channel sounder. Here, like the receiver would follow these three trajectories, and the data collected using trajectory 1 and 3 is used for training the model, and the data collected using the trajectory 2 is used for testing the proposed model. Now, coming to the solution part, this is the brief overview of the solution model. Yeah, given the channel impulse response, we first do the pre-processing, followed by the ML model. And for the ML model, along with the pre-processed input, we use the LiDAR data to train the ML model, and we get the predicted output. Here, during the pre-processing, the channel impulse response is transformed to power values corresponding to angle of arrivals. And why this pre-processing is required? Why can't we use a single ML model? The reason for this is whatever the LiDAR data that we have during training phase is analogous to monostatic radar data, whereas the channel impulse response that is collected, which corresponds to the each transmitter receive pair and across different delays, is similar to bistatic radar. So we need to convert this bistatic radar data to monostatic. So that is the reason we use this pre-processing. And also, like, the line of sight components between the transmitter and the receiver does not play any part for the depth map estimation. So, and this pre-processing is required to remove this line of sight components part. Before going to our solution, I would explain the baseline solution, which was proposed by Samsung, and they were the winners of this problem in the last year, that is 2022. What they do is, given the channel impulse response, this is a channel impulse response corresponding to a transmit receive pair, and for different delay taps. What they do is they use the Fourier transform step, and using that they get a beam resolution along the angle of arrival and angle of departure for both azimuth and elevation angles of 22.5 degrees. That is, whatever the resultant matrix or resultant beams would have a resolution of 22.5 degrees after this discrete Fourier transform step, and they remove the line of sight components. And to convert from bistatic to monostatic, what they do is they do this projection. So they remove the effect of the transmitter. For that, they project from this angle of arrival, angle of departure, and the delay dimension to just the angle of arrival and the delay dimension. Because of this, they are removing the effect of the transmitter. Then they convert this bistatic thing to the monostatic uh, data. For that, they multiply with a constant factor, which is given by this particular value. So This was the pre-processing that was done by Samsung, which is the baseline solution. So to briefly summarize their solution, they perform DFT step followed by removal of line of sight components, then the projection of the angle of departure to angle of arrival and the range dimension. However, the resolution of 22.5 degrees is not enough to distinguish all the reflective paths between the transmit and the receive pair, which would be helpful for the depth map estimation. For that, what we try to do is we try to exploit the uniform planar array structure, and we create the steering angle vectors with a resolution of 11.25 degrees. So as we increase the resolution, what it does is we would be able to distinguish the different reflective paths. So that means we are improving the beam resolution. And the other thing is, when we increase this resolution, the input dimensions to the ML model would be also increased, which would further increase the trainable parameters. So instead of considering 11.25 degree, we can consider higher resolutions. But why we restricted to 11.25 degrees is, for 11.25 degrees itself, if we consider a voxel grid size of 0.25 meter, the ML model input dimension would be of this size, 16 cross 16 cross 100, which would be 25,600 elements. So, and the available data for this problem, for this challenge, was around 3,747 samples.
1
Since
minute.
the number of samples, yeah, yes. Hello.
Yeah, it was 1 minute. You've got 1 minute left.
The available samples are very less, and this would lead to the overfitting. So that's why we restricted to 11.25 degrees. And the other steps is we again remove the line of sight components, and we do the projection. And this preprocessed data is given to this following ML model, which has two fully connected layers, followed by reshaping, upscaling, and the convolutional layers. And we also considered two other models. One is the baseline model, and one was just based on the convolutional neural networks and the transpose convolution neural networks, which did not give that good results. And the loss function that we considered was the custom binary cross entropy loss function. The results for the considered model is given in this plots, and the average chamfer distance for voxel grid of size 0.25 was around 1.7 for area 1 and 1.2 for area 3. And when the model was tested on the area 2 data, that is the testing data, we got a median chamfer distance of 2.59. Here we can observe the closer points we were able to observe, estimate better. So chamfer distance was very less, whereas the far away point, the chamfer distance was very high. And these are the outputs for the for the given model, and this is the lidar output. So to conclude, we proposed a uniform planar array based steering vector, which helped us to obtain higher resolution, which was given as an input to the ML model, and it was able to improve the results when compared with the previous year's solution. Thank you.
Thank you very much. Let's move on to the Q&A session. Can I ask Steve to moderate the Q&A session? Thank you.
Yeah, sure. So thank you very much for these results. If we start from the results, can you share the result again?
Yeah. Yes.
So the computed distance is dependent on the receive position.
You want this slide or this lecture?
Yeah, 17 is fine. Yeah. So this is something that we observed also last year, but thanks to your pre-processing now, it's much lower. The difference between the closest point to the farthest point. But do you have any intuition why the farthest point they provide poor result? Is it something
Yeah.
related to the SNR that is lower?
Yeah,
or...
yeah. One, yeah. That is what we like. We discussed like our team. What we thought was, as for the faraway points, the signal to noise ratio would be very less. Like the channel impulse response, whatever the input that we have got, that would itself would be very less value if you consider it. So that would play part, and that's why we thought the estimates might be poor, and for the faraway points, whereas the near points, that is not like the SNR would be good. So the same thing can be observed in the area 2, area 3 one. Since area 3 is nearby points to the transmitter, so here if we can observe, the area 3 average chamfer distance is very less. Whereas for area 1, the average chamfer distance is high. If you uh, look the data separately for area 1 and area 3.
So is area 3 closer to the transmitter?
Yeah.
I want to check now.
Yeah.
Okay, I see. Okay, interesting.
And what we think is maybe more data would help us to use a better ML model compared to the.
So you think that more data will be able to improve?
Would be helpful for would help us to consider a complex DL model, deep learning model, compared to the one that we have considered now, and
Okay.
that would avoid this overfitting thing.
Okay. I have another question. So it seems that your results are very similar to your evaluation. So the chamfer distance closely resemble. So the chamfer distance in a data set that you haven't seen in training, it's very close to what you obtain with the training data. So I wonder, do you think that if we move to a complete different environment, will the model still work? Maybe with some fine tuning of the ML model, or so? Do you think that the ML model is robust enough to be used in different environments?
Yeah, maybe one possible thing that we can do is keeping this ML model itself. We can use certain amount of extra data to train the ML model further instead of starting from the scratch. I think in that way this ML model might be helpful.
Okay.
Okay. Thank you
so
very
much.
much. That's the end of the Q&A session.
Thank you.
Thank you. And last but not least, we will have the explanation and presentation for the problem statement multimodal V2V beam prediction from Arizona State University. Professor Ahmed, the floor is yours. Oh, Professor Ahmed.
All right, so do you see the slides?
We don't see the slides yet.
Okay. Okay, so let me share maybe the full screen. For some reasons, okay. Do you see the
Yes, we can see it now.
full slide now? Okay, perfect. All right, so thanks everyone for attending, and thanks for those who participated in this competition. Multimodal V2V beam prediction this year jointly with ITU, that we're organizing jointly with ITU, and just quick kind of overview about the competition. So what we were particularly interested in this competition is to investigate whether we can use different multimodal sensing data to guide the communication beams and the alignment of the communication beams in V2V or vehicle-to-vehicle communication systems. So as you probably know, so if once we start using millimeter wave communication systems, then we need to typically use large antenna arrays and narrow beams, and aligning these beams require a lot of training, right, to find the best beams at both sides. And if this is particularly a high mobility scenario like V2V, where both vehicles may be deploying beam forming, or at least one of them, then this would typically be very challenging because you don't have maybe enough time to, these vehicles don't have enough time to find the best beam. So the question is, can we use sensing information such as positions of the vehicles, visual data, LiDAR, radar, and so on, to provide at least some, guidance for the beam prediction, or directly predict the beams at the communication terminals. So that was motivation, and so more specifically, the problems that we had in this particular competition is that we had sequences of data. These sequences basically include different sensing modalities from position, vision. Now the dataset has also LiDAR and radar, but that we had in deep sense. But in this competition, we restricted it to position and vision. Okay, so in addition to the communication beam information at the receiver side. And now out of these sequences, we had short sequences now that we finally have as our training and test set. So these short sequences, each sequence has 5 samples, and these 5 samples have both like position for the transmitter, position for the receiver, and visual information from 360 cameras, and in particular taken from as like front view 180 degrees and back view 180 degrees. And these are front and back cameras, or basically front and back views from a 360 camera deployed at the receiver vehicle. So in summary, we have a transmitter that carries a millimeter wave. We have a vehicle that carries a millimeter wave transmitter that transmits in all directions. And we have a receiver that has a vehicle receiver that has a millimeter wave, that has basically a box of 4 sides. Each side has a 64 beam forming cool book. So we have a total of 256 beams from the 4 sides. Okay, that can scan basically 360 degrees with beam forming, so the receiver can find the transmitter anywhere. And also from the visual data, so this receiver has a 360 camera, and then basically from that we extracted the front and back view at this receiver, and then we have the position of the transmitter and the position of the receiver. Okay, so that's the sensing information for the position and vision are fed as input to this to this basically competition, or this machine learning model that the competition focuses to kind of design it to be as efficient as possible in predicting the beam that was given as labeled in the training set. And in particular, so with 5 points, 5 samples spaced 200 milliseconds from each other, we want to predict what is the best beam in the future, and in particular also 500 millisecond in the future. And as a way to kind of connect the result of this prediction with the actual communication objective, we defined what we call average power loss objective, or basically a loss function, or score also. So the scores that we used in evaluating the different solutions is what we call average power loss. In particular, it the general idea here is that measures what is the loss in the power that we achieve using the predicted beam compared to the ground truth beam. All right, so using basically this is again the definition of the competition, and this competition used 4 DeepSense 6G dataset scenarios. And so DeepSense 6G is a dataset that we built and published last year, and we keep adding more and more scenarios to the dataset. It is a multimodal sensing and communication data. It has sensing modalities from vision, position, LiDAR, radar, IMU, and for the communication we have beam power, and very soon we'll have IQ data as well. And so this competition used 4 scenarios out of this dataset. All right, so with that, very happy to announce the winners of this competition this year. So the first team is BeamWise, and the average power loss they achieved is minus 6.26 dB. Of course, the closer to the 0 dB is the best. And the second team is Hyperion, and the average power loss achieved is minus 7.08 dB. And last team is Acer Othman, and average power loss is minus 9.52 dB. So congratulations to all the winners. And now I guess I'm very excited to listen to their solutions.
Okay, can we call for Team BeamWise then to do your presentation?
Okay, you should see my screen.
Yes, we can see your screen.
Okay, hello everyone. We are PhD students from University of Bologna, KAUST, and the University of Electronic Science and Technology of China. And we are going to present our solution for the multimodal beam prediction challenge. We will start with a brief introduction to the problem, followed by data preprocessing. Then Diego will discuss the model and model training, and finally the experimental results. Here a brief introduction to the problem. In vehicular-to-vehicular communication, the increasing demand of data requires the use of higher frequency bands like millimeter wave or terahertz, which translates into a smaller wavelength, allowing the deployment of more antennas than before. However, when the number of antennas increases, we have narrower beams due to the higher beamforming gain, and thus the beam tracking overhead becomes challenging with the traditional methods. Therefore, as Professor Ahmed already said, sensing-assisted communication with the use of multimodality sensors has the potential to further improve the beam tracking performance by reducing the overhead. And in this challenge, the objective is to predict the future beam index 500 milliseconds ahead, given a sequence of 5 samples from 2 modalities, which are RGB images and GPS, spaced 200 milliseconds apart, as you can see in the right image. And the evaluation metric is the power loss, which quantifies how much power we lose by selecting a suboptimal beam. Regarding data preprocessing, we first normalized the images according to ImageNet, and then applied image augmentation, as we will see further. And for the GPS, we tried to extract features from raw data, like relative velocity, curvature, acceleration, and so on. And here you can see an example within 4 seconds of measurements picked from the development set, where we display the coordinates of both vehicles at the top and the velocity and curvature features at the bottom. And to avoid fluctuation in the data, we use the Kalman filter to obtain a smoother data representation. And now Diego will follow up with the model description. Please, Diego.
Hi, everyone. This is the diagram of our model, and this is a model based on a network called Transfuser, which is a well-acknowledged solution for autonomous driving, and it consists of three main parts. The first part is image processing. It takes images from the front camera and the back camera of one of the cars, and we send 5 images from each camera through the network, who will do the processing. And this network is an efficient NetB3. We choose this network particularly because it has an amazing trade-off between performance and number of parameters. And together with this image data, we send also the corresponding GPS data for each car. And this data is processed in this network you can see in green in the bottom, which is a sequence of linear layers. However, in the middle of those networks, we pick intermediate features and we fuse them using transformers. And particularly in this project, we are using swim transformers. The swim transformer, it has a good characteristic compared to the original transformer. They take the data and combine tokens. However, the self-attention from the original transfuser, it has a quadratic complexity regarding the number of inputs. And the swim transformer, on the other hand, it is linear related to the number of inputs and quadratic to a parameter called window size. But this parameter is generally a small number. And then we pick intermediate features, fuse them, and send them forward through the network. And after this, at the end, we'll have a MLP, which will be doing the selection of the appropriate bins. And regarding the training, we used really standard procedures. We used cosine learning rate schedule to help to avoid overfitting, exponential moving average to turn our model more robust to outliers. We used the cross entropy laws on the bin prediction. And another thing that we added is the softening of the bin index, because we want to have different penalties for bins that are closer to the correct bin and far from the correct bin. Then we attributed more weights to the bins closer to the central one. And also to improve performance, we applied image augmentation. As is standard for video processing, we applied all the augmentations through the same augmentation to all the images for each sequence. To avoid deterioration of positional data, we didn't use any geometric augmentation, and we used only value augmentation, from where we can mention the brightness, contrast, Gaussian blur, gamma correction, hue, and saturation.
Okay, thank you, Diego. Now let's come up with the experimental results. Here you can see the comparison between the baseline solution provided by ITU against our best model. And it is noticeable from the tables below that our model provides an enhancement compared to the baseline. In fact, you can see how the top one accuracy doubles, and the average power loss score is close to 0 across all scenarios. At the top, we show the loss and the average power loss score during training. And we can see that our model converges in less than 20 epochs. And to give a visual example, at the top left, we selected a random sample from the dataset and compared the prediction of our solution against the baseline. And we can see how, in this case, our model directs the beam towards the transmitter, whereas the baseline prediction is not accurate in this case. And in conclusion, we have developed a transformer-based deep learning framework that relies on multimodal sensory data to predict the beams. And the transformer, as Diego explained, has been employed to fuse the features in different layers. And our solution helps in reducing the beam tracking accuracy, and we achieved higher performance compared to the baseline solution in terms of both average power loss and accuracy. And finally, our model can be easily adjusted according to different sizes and needs to a specific problem. Thank you.
Thank you very much. Let's move on to the Q&A session.
Right.
Yes,
So,
Professor Ahmed, thank you.
yeah, right. Thank you. Yeah. So first, thank you very much. Really great work. Congratulations again. So I'm just curious. So did you try to compare the performance with only vision, only position, and then you showed, of course, the fusion, right, of the two. So any insights on that you were able to get on like what performance you would have achieved if you just used visual data or position data?
Okay, this is a thing that we have still further to discover, because we really focused on finding the best solution with all the data available, like all the sequences and both images and GPS modalities, because we think that, okay, maybe when the vehicles are closer, maybe the images can be useful compared to the GPS that has latency and so on. So maybe the model is powerful enough to discover, to combine with the transformer, combine both images and GPS to find the best beam when the machine is closer, when the vehicles are closer each other. Whereas images become less important when the vehicles are farther away, and then the GPS could be a useful modality to use. And the transformer should be intelligent enough to wait and to discover which feature is more important than the other.
Thank you. Yeah, really great work. So sorry, I don't have actually more questions, but I wanted to make two general comments about this competition, just as concluding remarks, 2 or 3. So one, just a general point that we noticed in, I think like as questions also that came to us as part of like when we published the challenge set, is like the score that that most teams were getting internally is different than are different than the scores that we send them as a part of the evaluation. And one main reason is that most teams basically used overlapping sequences in the training and test set. So and if you overlap the sequence, or basically if you take the same long sequence and then slide a window and then take part of these short sequences as part, as a result of the sliding the window in the training, and part of them in the test set or the validation set, then you get some leakage between the training and tests, and then the test would basically, the model will somehow memorize, and this improves the test results that you get. While in the evaluation, what we did is that the scores that we were sending were based on, again, a test set that has no overlap with the training set, right? So that's why, or the challenge set has no overlap at all with the training set. So that's why, the model was really performing basically on what it learned already, not what it may have memorized. So this is one comment. That's the comment on the results. Now, just last comment I wanted also to mention here is that this competition, like last year, will now move to be another machine learning task on DeepSense, on the DeepSense website. So for any team, either from the teams that participated in the competition or from anyone else, any other research group or academia and industry that's interested in participating in this machine learning task. So this will stay open on our website, so they can always submit their contributions, and we will evaluate and we'll add to the ranking. So we'll have still the ranking leaderboard on the website, and again, it will stay active. So the competition itself ended, and the scores are there, and the winners are announced, but it will now transform into another task that will stay open. So yeah, with that, I thank again everyone, and back to you, I guess. ITU. Thank you.
Thank you very much. I'd like to next call for Team Hyperion. Please share your screen and start your presentation.
Okay. All right.
Perfect. Please turn on your camera as well. Thank you.
Oh, it's not on. Okay. Right. Okay. So. Okay. So the multimodal V2V beam prediction challenge. So as you can see, my title doesn't say multimodal because I only use the GPS data. This is due to multiple reasons, among them being the compute resources. Yeah, so the introduction, I think, is well understood by now. So, yes, we were given 5 GPS coordinates for 2 vehicles, they receive and transmit. So we're supposed to predict the 5 being 200 milliseconds apart. We're supposed to predict the beam in the next 500 milliseconds or half a second. So since I use GPS data only, here's how I went about it. Okay, so this is the representation of how I should explain how I generated my data. So we have 2 vehicles at each and every sample, X1 through X5. So I had to generate a lot of information that comes from the latitude and longitude of these 2 vehicles, so that will help me in coming up with the beam. So the distance between the units within the samples. So in this case, I mean the distance between the transmitter and receiver within that X1, the same to the rest of the samples. The distance covered by each vehicle, the cumulative distances. So in this case, I mean the cumulative distance from X1 to X5 of each vehicle and the cumulative distance between the vehicles from X1 to X5. Then I had to find a way to know whether the car is accelerating, decelerating, or probably static. So that's the acceleration. So as you can see, I don't know if it's visible, I selected at 0.4 seconds, that's 400 milliseconds, and 800 milliseconds as points for velocity 1 and velocity 2. That's how I'll get the acceleration. And then that should tell me whether the car is slowing down, accelerating, or stopped. And also the average distance that each vehicle has covered. And the average distance the 2 cars maintained in that particular time measurement. So furtherly, I had to normalize because I was using LSTM. I use a standard scalar, but also had one challenge. Well, we all did actually. So the target ranges from 0 to 255. So you have to restrict the model to provide the outputs in that range. But then you have to consider the fact that these values are circular in a sense that 0 is very closer to 255 than it is to something like 50. So I had to break down the beam, the 0 to 255, into its sine and cosine transformations using this formula here. So these values range from -1 to +1, both the sine and cosine transformation. And then I had to a function that can reverse from these 2 particular values to the original beam that ranges from 0 to 1. I mean 0 to 255. So having that in place, let's go to the LSTM itself. So this was the normal bidirectional LSTM, nothing complex, just kind of 4 layers. Trained it on the mean absolute error as a loss. So I also trained it on GPU, just to take a note. So as I said, this LSTM doesn't. It takes 2. I mean, it produces 2 values. Since I have transformed the single beam value into 2 components, the sine and cosine, that range from -1 to 1, I had to use the hyperbolic tangent as the activation function at each and every level, which works well with GPU too. So the LSTM itself provides the sine and cosine components of the actual beam itself. I guess that solved the problem of the circular nature and the fixing the range of the beam themselves. So evaluating, there was this average power loss, which I think I have to mention it here. I had an issue with it because, okay, so APL was 10 times log to base 10, then with the ratio of the predicted beam and the actual beam. So, okay, so from this, if the predicted beam is higher than the actual, that's actually a positive. Then if it's lower, then it's a negative. So in a course of 100,000 values, you have a mix of positive and negative values. So looking for the average in the end, that kind of contradicts because summing the negative and positive values gives a lower value. So I kind of saw that this didn't give me actual results. So I was considering mostly on the average beam index distance, which considered the mean, the absolute error, but considering the fact that this is a cyclic data. So I also used mean absolute error to see how my model performs. All right, so to make a comparison, I used the random forest model tool to compare the LSTM with, because random forest is good at capturing the range. So there was no need to use the sine and cosine components in this case. So all the training data given, I took 80 for training, the 80%, then 20 for evaluation. So you can see the average power loss came out as a positive. So yeah, this is the fact that I just explained about. So I was considering the average beam index distance, which was 2.42. Considering the benchmark gave an 11.7 or something like 14. So I saw this as a very good improvement. Yeah, so random forest was somehow good, but on plotting the distribution of the actual and the predicted beam values, LSTM showed a very good matchup between the predicted and the actual. So this is also another regression report, analysis plot. So still, we can see LSTM does better than my comparison algorithm. So conclusively, LSTM did a good job. Preprocessing and feature engineering added some success to the model because I tried without anything to see how it actually does. It didn't do well, so obviously processing did a good job. So I think that should be it. So just to wrap up, improving the model architecture should be something to look at in the future. And building separate model, so in this case, adding the image data, but also importantly, to follow through the expected latency between the actual capturing of the data and the recording, so that the latency can be incorporated in the preprocessing of the data. Yeah. Thank you.
Thank you very much. Let's move on to the final Q&A session. If I could again ask for, thank you.
All right, yeah, sure. So thank you very much. Excellent work. Just maybe quick clarification on your point on the average power loss. So in fact, okay, yeah. So so if you go back to the slide, so the average power loss is defined as 10 log 10 P prime over P. So as P dash P prime is basically the power, not the beam, right? Is the power of the predicted beam, right, compared to the power of the ground truth. So maybe, just in case this is not clear. So then the average, the achievable power using the predicted beam is always lower than the ground truth power, or the power using the ground truth beam. So that's why this is always, is going to be less than 0 dB. Okay, so this is just clarification here, and so can you comment maybe on the complexity of the model? Of course, you use only position, right? So I would expect you had relatively low complexity and low latency, I would guess.
Yeah. Okay. Considering the fact that I used the as GPU in training. So without GPU, that would take in the training process on the 80,000 data points, which I think I created more than 40 something features from the initial GPS coordinates. So without GPU, that should go. The training process went to around 40 to 50 minutes, but with GPU, went to like 4 minutes to 5. But the complexity of the architecture itself, now it's quite a simple architecture.
Yeah.
So maybe the whole training process, but for a few predictions, I think it's a very simple approach.
Great. Yeah, this is a very good work. So basically, I mean, I just wanted to highlight this kind of, overall not particular for you, but this kind of interesting, trade-off between complexity and performance as we look at all these multimodal sensing, from position to vision to LiDAR to radar to other sensing modalities, and how they could be useful to different communication tasks. And the tasks, so definitely a very important problem is, or direction is to look at, how to compromise complexity and performance and the trade-off between the two. So thanks again, great work. You are now the winner in 2 competitions, right? So it's mastering position data, I guess. Congratulations.
Thank you.
Okay, thank you very much. I'd like to now pass the floor to Vishnu for announcements.
Okay, thank you very much. That is an excellent set of presentations. And thank you to the hosts. It is a tough job. So thank you very much for all the hosts who are here today. I am going to do the tough job of announcing these winners. As you can see, we have 3 competitions today. There is $, going out. First cash prize is 500 Swiss francs, second 300, and the last is 200 Swiss francs. You will also get this very nice certificate, which is signed by our Secretary General, Ms. Dorin, and Onoe-san, who is Director of TSP. So let us see. First, this certificate looks like this. We will look at the V2V beam prediction problem. And there, we have a second runner-up for this challenge. And once again, thank you for the nice discussions, Professor Ahmed and the colleagues here. That was very enlightening discussions. We have congratulations going out to Hyperion team for this second place. Thank you very much and congratulations. And then we have, without much suspense, we have first place winner for this particular challenge, first place winner. And that one is BeamWise. Congratulations to BeamWise. Thank you so much for the nice presentations today. By the way, that was a very interesting solution as well. Very nice solution, very exciting solution. Moving on, we have 3D location estimation, RSSI wireless LAN problem statement. There we have one winner, and there the winner is Polaris. Congratulations again, and that too, a very nice analysis. Thank you so much for that solution, and congratulations. And finally, I believe this depth estimation for 60 millimeter wave systems. We have one winner, and the winner for this particular problem statement is Jayant. Congratulations, Jayant, for the nice build up on previous year's solution, previous year's 2022 solution. That was a very nice step up from that solution. Thank you so much, and congratulations again. And on behalf of everybody here, that was a very exciting challenge. I mean, the depth of discussions, even though we had a lesser number of teams, the depth of discussions, I would like to point out, that was fairly deep. So thank you so much. And as Mia pointed out in the beginning, journals, ITU journals exist. So please consider to write up your solutions and submit for the journals or ITU journal or the whatever academic publications of your choice. Thank you for all the participants, and back to you, Mia.
Thank you very much, Vishnu. I'd like to now call for Professor Ahmed to make closing remarks.
All right. So yeah, I just want to thank you again. Thanks again, everyone who participated in this session and in the competitions that ITU organized, and collaboration, of course, with all of us, and that was very exciting. And it's really great to see, how these competitions also motivate the research in very important directions, right? From depth map estimation to positioning to millimeter wave beamforming, which kind of, again, all are kind of key enablers for 6G and beyond. And see basically hopefully how this also result in future publications and encouraging research and cycles of research to come. So again, very exciting time, and a lot of interesting contributions that we have seen today. So yeah, with that, thanks everyone again, and see you again in future competitions.
Thank you very much. Again, from myself, I'd like to thank all the hosts of the problem statements for joining today's session, as well as congratulate and thank the winners for doing their presentations. And finally, I'd like to thank the audience for sparing your valuable time to join and attend today's finale. For the AI and 5G challenge, we do have a lot more coming in the near future, so please check the AI for Good program page for more details. You can again interact with us and other participants on the Challenge Slack channel, so we look forward to seeing you there. Thank you again for joining today's session, and I wish everyone a very good day.
Thank you. Bye-bye.
Thank you very much. Have a nice day.
Thank you. Bye-bye.
Thank you.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.